Hi everybody. In this lecture we're going to start in on our basic statistics lectures. This is broken into a lot of smaller components so that it doesn't get too overwhelming. So we're going to start with descriptives. Descriptives being the very general things that a statistician can calculate. And to give you a very brief overview of kind of statistics in general. And this is very brief, but enough to get you by to understand kind of what's going on. So we'll talk about parametric versus non-parametric statistics with a brief reminder about what are the types of data that people can have. And parametric and versus non-parametric, like which one I should use, is really all about a dependent variable. So think about that as like all about that base, but it's all about the DV. So the DV often dedicates or tells you which type of statistic to run, non-parametric versus parametric. The DV is like the scale of the DV, the types of the DV, or even whether or not it is normally distributed, or if it meets the assumptions of the data, which we'll get to in a couple of lectures. And then after you make that distinction is when we get into the IV tells me what type of statistic to run within parametric versus non-parametric. So we're going to do a little bit of both this year. And then this lecture is about descriptives, and the next lecture will be about inferential statistics. But really there's a distinction there between just describing the data and inferring things from the data. So first let's start with the types of data that a person can work with. Now there's obviously qualitative data, but if we're talking about quantitative data, we're going to break this into what's called the NOIR system, nominal, ordinal, interval, and ratio. So our non-continuous, our discrete data types are nominal. Okay, some people also call this categorical, where data is clearly defined into categories. So this often is labeled data. So like we have dogs and we have cats. So things are one or the other, but not somewhere in between. Ordinal data is usually considered ranked. So I always think about the Olympics for this. So and Phelps is just a great example of the Olympics, where sometimes he wins by a lot, sometimes he wins by a little, but he still wins. So we lose the information about the spacing between the data points. We just know first, second, third. Our continuous data, which is mostly what we'll work with this year, often is considered interval. So interval data is ordinal data with equal spacing between the numbers. So I know that 1 to 2 has the same space as 2 to 3. And 2 is twice as much as 1, and 4 is twice as much as 2. But there's no true 0 point. 0 meaning an absence of something. It's difficult to think about height, a 0 height, like a no height. But in theory, it could have no height. But the most of the interval data we work with is Likert or Likert scales, where there's no real 0. 0 doesn't mean no opinion, although we can try to make it work that way. It doesn't really mean, most people pick that as neutral. Temperature is a scale that does not have a true 0, because there's never an absence of temperature. It's just really cold. Ratio data is sort of held up as the golden standard. It's where we have equal space between the numbers and a true 0 point, where if I could have 0 time, that would mean literally no time had passed or no difference in times, that sort of thing. And so we tend to treat interval and ratio data as the same thing for statistical purposes, although they really aren't. But most of the stats we're going to run this semester you can do on either type of data. So the big distinction here is this non-continuous data is non-parametric, continuous data is parametric. So our parametric statistics are things that we're going to use on continuous data, DVs, continuous dependent variables, interval and ratio data, and the numbers are relatively continuous. That does require we have more assumptions to check, which we'll talk about in our data screening section. And that's most of the statistics that you'll use and you'll see published. So ANOVAs, regressions, t-tests, correlations. Non-parametric statistics is used on all data types. So there's this weird assumption that you cannot use continuous data with non-parametric stats, and that's a lie. Non-parametric stats is actually more flexible because it allows you to use nominal and categorical and ordinal data, but also continuous data when they don't meet their assumptions. Generally, this is done when you don't have continuous data, or your continuous data doesn't meet the assumptions of parametric statistics. Because non-parametric statistics are more powerful, meaning they're better for you, when your data doesn't quite meet the assumptions of a parametric test. So there are advantages to doing non-parametrics. Not all data works for that, though, and they are a bit more complicated sometimes. So it doesn't require the same assumption, so they don't require that your data be normal, is the big assumption. We'll do a little bit of this, some chi-square analyses, some log regression. And under chi-square, you get into like ratio tests. So you've got odds ratios. And then if you're in the clinical field, you'll have things like relative risk, likelihood ratios, positive predictive values. Those tend to be kind of thought of as non-parametric tests. We'll also cover a little bit on ROC curves. So get into descriptives. So what can I do with all of this data that I have? And generally this is going to be continuous level descriptives, although we'll talk about some non-continuous descriptives. So what descriptive stats do for us is they create a picture of the data. They describe the data, hence the name. So we can calculate a mean, so I won't bore you to death with the definition of the mean, but it's the average of all of the scores. And then some sort of non-parametric versions might be I calculate the mode if I have categorical data, which data point happened the most often, or if I have very skewed data, which we'll get to in a second, but skewed data has a lot of extreme values, or maybe a couple of extreme values. The median might be more interesting. And that's why they use median housing prices and median incomes in areas, because you're going to have a lot that sort of center towards the bottom and a few high outliers. So if you ever hear them talk about the median income in Dallas, obviously that's going to be biased a lot by the fact that there are somewhere between 3 and 4 professional teams that live in Dallas. So they can't use the mean because that would be really distorted by the fact that they have a professional basketball team, football team, et cetera, et cetera. Now, if I have that mean, that's a useful number, but sometimes I want to know how much that varies. So the mean is just one data point. Sometimes it's called a point estimate. And it just tells me the average score. So if I tell you the average score on the first test in any class is a 75, it makes you kind of nervous. That's a C. But what variance does for me, and even more so this next slide, is it allows me to see how much those scores vary. So sometimes these are called measures of central tendency, like the mean, the median, and mode, and then measures of dispersion, so how much these distributions spread out. And that is a really useful piece of information. So what I can do is take my mean and calculate an average distance from that mean. So the variance is an average away from the mean, or it's close. Mathematically. And what that does for me is it tells me how far scores are away from the mean on average. The biggest problem with variance is that it's squared. And we won't get into the reason why, but it's a mathematical issue that you can't just find the actual distance from the mean and then average, because otherwise it would add up to 0. So what we do is we square this stuff. Well, squaring it solves our math problem of adding up to 0, but it makes it for another issue, which is if I tell you that the average score is 75 points, and then the variance, or the spread around the mean, is 25 points, that's get a little confusing because that's 25 squared points. So the simplest solution to bring it back into the same scale range is to take the standard deviation. So the standard deviation, or the standardized variance, is the actual average distance around the mean. And so what that does is it goes from being in squared units, so variance is squared, to not squared units. So that means that the scores would be about 5 points from the mean. So on average, people are scoring somewhere between a 70, 5 points below, and an 80, 5 points above. And when we get into z-scores here in a second, this is a really useful thing to know, because we can standardize scales completely into Z, which is how standardized testing works, or we can use this information to get a feel for how well we've measured our score. So when we talk about confidence intervals, we'll look into a little bit of how we can use the standard deviation as a number that means more than just the spread. Now, standard deviation isn't perfect. It's an estimate on the sample. And we don't always necessarily want to estimate from the sample. Sometimes we want to get a good idea of what the population's numbers might be. For the mean, we just assume that the population has the same mean or a similar mean. But for the standard deviation, all we've done is measured a specific sample, one sample. So how can we tell what the spread of everyone in our population might be? So this is a question of how can we measure the actual spread around the mean for everyone versus standard deviation is the spread around the mean for this group of people. That's where standard error comes into play. So standard error is the standardized variance, or the standard deviation. And it's an estimate of standard deviation for a population, for the larger whole of people. So what you do mathematically is you take that standard deviation, you divide by the square root of n. Now n is the size of the sample for your study. So the more people you have, the more precise you're going to be. And what that does is it allows us to estimate a population estimate. And so that's going to be really important when we get into t-test and hypothesis testing. And so there's a couple of different numbers that you might see reported. This is APA style. Standard deviation is going to be listed as SD. And so remember that that's the average distance around the mean for this sample. If you see standard error, that's going to be the average distance around the mean for the population, or what we're estimating it to be given our sample size. Standard error will always be smaller because we're dividing by n, or the square root of n. And it's a really useful number for hypothesis testing, which is all about the population, comparing to a population. Standard deviations are more useful when we're just talking about this one group of people. And so if you want to get a better grasp on this idea and sort of what's about to happen next, there's a video. I always call it distribution bunnies, but it's put together. It's to understand the central limit theorem. The central limit theorem is this idea that as n increases, distributions become more normal, and the spread of the variance, the standard deviation, and the standard error, all three of them are tied together, gets smaller. And so what happens is the larger the sample size, the more the distribution kind of squishes up and gets skinnier. It talks a little bit too about why we use standard error, but it's a really great video. I can't show you video in a video because it freaks out the computer, but you should be able to get to this link opening up the PowerPoints. You can also Google central limit theorem bunnies and you'll find it. It's the first link. It's also just fantastically silly and just great. And so if we're going to take the mean and this standard deviation thing, how can we visually depict that information? So what we can do is we can make a histogram, which is a graph version of it, or a frequency table, which is a table version. Okay. So what a frequency table does is it shows each individual data point and the frequency of those points. So frequency tables, just so you get the distinction here, are much more useful for categorical or non-continuous data. How many cats did I have? How many dogs did I have? And histograms are much more useful for continuous data that shows me the distribution of the data. So back to that split where we have that sort of non-continuous things that we might depict in tables and continuous data that we might depict in a histogram. Then when we get to graphs, we'll talk about some other types of things that we can display the data. And so histograms are really helpful in showing you the distribution of the data. So distributions are where we're looking at a continuous, usually continuous values of the data on the bottom of an x-axis. I have that on a slide here in a second. This slide, which should be a little early, So the values are across the bottom, or the x-axis, and the frequency of the data is up the y-axis. So there's no real y here. Normally people think about having to plot two variables. Histograms are just one variable being plotted with values across the bottom and the frequency of those values up the y-axis. And so this is helpful because it allows me to see what the data looks like on usually a continuous scale. You can make histograms. This is the picture version, so it's a histogram of non-continuous data, but personally it just doesn't make a whole lot of sense unless I just want to see that one bar is taller than another, but percents do that just as well. Because there's no real reason to order one bar in front of another when they're categorical, whereas here on a continuous scale there's a reason to have them in the order they're in across the bottom, right? Because they're increasing. So let's back up. So a couple of descriptions of types of distributions. So we can have unimodal distributions, meaning they have one hump. Bimodal distributions, meaning they have two humps. Multimodal distributions, 3 or more humps. And rectangular distributions, which tend to be shaped like rectangles. Sometimes people call this the uniform distribution. I think rectangular is a better name for it because it describes it visually a little better. Uniform to me, I think military. But uniform is a rectangular distribution. And so that describes the number of humps a distribution has, or the number of modes, if you want to be more technical. Normal, or the so-called normal distribution, is centered around the mean, which means hot dog fold style. You can take the distribution and fold it in half and it's the same on each side. It is unimodal, so it could have a distribution that folds in half that has 2 modes, or is bimodal, but that's not the normal distribution. Okay, the normal distribution has one hump, folded in half, its hump is the same on each side, and so therefore it's symmetric. So let's look at some pictures here. Here's a unimodal distribution with one hump. This would also be the normal distribution because it's centered at the mean, the average score, and is the same on each side. A bimodal distribution here with 2 humps. Multimodal distribution with 3 or more humps. Now, bimodal distributions, the technical definition of them, or multimodal, is that they have more than one mode. And one issue I have with that definition is that if I think about a unimodal distribution, let's look at this one. So this distribution is it's unimodal. It's got one mode. But if I think about, let's say 8 and 9 were equal here, so they were equally high. I think I can do this. Let's make it green. So let's say that they're equally high here. So I have 2 modes. 8 and 9 were the highest numbers. That to me is not a bimodal distribution because it still just has one hump. I can't draw on this very well. Okay. Now if I had a distribution that went up like this and then had a second hump here, it would technically be unimodal because it would only have one most often point or mode here. But it clearly has 2 humps. So I don't like the technical definition of unimodal and multimodal being the number of modes because visually that doesn't always match what you're looking at. So I always just think about it like camels. How many humps does it have? And there has to be this space here in the middle for it to be multi or bimodal, where it has one clearly defined hump, the valley, and then another hump. So talk about the normal distribution now. This is one of my favorite statistics graphics because it's just funny. So the normal distribution here centered at the mean. If it'll let me pick a color here. There we go. Centered at the mean, hot dog fold, equal on each side. That's very handy for standardized tests because I could say that you fall right here on this distribution, which is above the mean, and how many percent people are above you and how many percent people are below you. The paranormal distribution is just kind of a joke with a little ghost here. Happy face ghost. And I think that's funny because it's a ghost, but also it's funny because the normal distribution is so not what you'll find in real data. With enough data points, things are close enough to normal. That's part of the central limit theorem. With at least so many data points, it approximates normal. But often when you're doing real research, normal distributions are few and far between. at least when you work with people. Social sciences get a lot of crap sometimes for being the soft sciences. So I always tell chemistry people that they have it lucky because, you know, it's not like you're going to come into the lab and they get chemicals aren't going to react because they don't feel like it that day, whereas people do have that particular issue. So, anyways, so the normal distribution, it's unimodal, symmetric, and centered over the mean. All right, look at this picture. Let's talk about what happens when distributions aren't normal. So skew. Skew is a really helpful piece of information to tell you how far away something leans from normal. So skew is a lean. How far away are they leaning? So you can pick politics if you want. Negative skew is, it's all about the tail of the distribution. So the distinction between parametric and non-parametric is all about that DV. This is all about that tail. So scores on a negative skew actually pile up on the positive end, but the tail is on the left side. Okay. Sometimes that's called a ceiling effect, where all the scores are at the top of the distribution, none at the bottom. Positive skew is when the scores are all on the bottom of the distribution and the tail is on the right. So sometimes that's called a floor effect. Okay. That is totally backwards from the way you want to think about it. You want to think negative skew, all the scores are at the bottom. That's completely wrong. So remember, it's all about where the tail of the distribution is, or where the scores are missing. That's the way I think about it. Or where the scores, the extra scores are that are causing it to look lean. Now when I learned this, I learned it with a cat. And so if you always draw the little cat head on the top of the distribution, the skew is where the tail of the distribution is. So this would be a left skew or a negative skew because it's on the bottom end of the distribution. Other term we're going to use to describe distributions is kurtosis. It is how different from normal up and down instead of left and right. So mesokurtic distributions, or this one here in the middle, are normal. So mesokurtic meaning normal distribution. Leptokurtic distributions are taller, so they're sort of squished in. And then platykurtic distributions are flatter, they're flattened out. Okay. It's still all about the tails of the distribution. So leptokurtic distributions have fatter tails, and platykurtic distributions have skinnier tails, but really, if you think about this picture, it's about how squished or flatter the distribution is from normal. And the very famous picture to describe kurtosis is that a platykurtic distribution looks like a platypus, and a leptokurtic distribution is leaping kangaroos. So this is from one of the books that first presented this, and so platykurtic distributions are flatter, leptokurtic distributions are taller. And so that should sum up our first lecture on some basic statistics and distributions. And so now you should go watch the video in either R or JASP on how to calculate and create these pictures.